Thank you for the invitation to come speak to you today. So today, before I begin, I'd just like to thank the undergraduate and graduate students in my laboratory, including these students up here, as well as collaborators at the University of Wisconsin-Madison and the Global Lake Temperature Collaboration. And so you may have heard that we're currently experiencing our 6th mass extinction. And the reason that we know that we're in a mass extinction event is because current extinction rates are about 1,000 times the natural background level. And as opposed to the previous mass extinctions, this one has been caused by one species and happens to be humans. And 3 major factors that are contributing to this mass extinction include climate change, invasive species, and habitat degradation. And so there are predictions that 1 in 6 species could go extinct. And so what I want to focus on today is looking at the aspects of climate change, and we'll build up to understanding how that may cause impacts on biodiversity. And so just to introduce you to climate change, you may have seen this graph. This is known as the hockey stick curve. And what we have here on the x-axis, we've got year from 1880 to 2010. On the y-axis here, we've got carbon dioxide concentrations. And so in red and yellow, you can see carbon dioxide concentrations have been increasing for the past 130 years. And in fact, they've now reached past 400 parts per million, and they've said that this last week was the last time we'll ever see carbon dioxide concentrations below 400 parts per million, which hasn't happened since in the past 165,000 years. And global air temperatures have also been increasing as these greenhouse gas emissions have been increasing. And so the IPCC, which is a collection, it's an intergovernmental panel on climate change, is looking at how climate may change in the future. And so here we have projections going up to 2300, and these are global air temperatures. And in red here, what you see is the prediction of increases in temperature of about 8 degrees Celsius if we continue emitting greenhouse gases at current rates. However, if we stabilize greenhouse gas emissions in this blue line, by 2030, we could see an increase of temperatures less than 2 degrees Celsius. So stabilizing greenhouse gas emissions could have dramatic impacts on how much air temperatures may increase globally. And so first, just why would we study climate change and what are the impacts of climate change? A report just released yesterday suggested in the last 20 years, 600,000 people have died because of extreme weather events. And that has cost, these extreme weather events have cost $1.4 trillion just in the past 20 years. And so why would we want to study lakes? So that's sort of what I'm interested in. Canada holds 20% of the world's fresh water, and we have approximately 3 to 7 million lakes. We have so many lakes, we can't actually count them all, especially in the north. We don't know how many lakes we do have. And it's a non-renewable resource that is really quite indispensable, as California is really experiencing right now with these major droughts. Lakes provide a lot of potable water and recreational and economic, social, and cultural importance. And today I'm also going to talk about fisheries, and that's an important food source, recreation source, and the fisheries industry is worth billions of dollars within Canada. And so I'm going to talk about today how climate change can affect biodiversity in lakes. And I'm going to go about doing it in 3 different ways. So first, we're just going to talk about the past. So how has climate already changed in lakes around Ontario, but also around the world? And then how might that impact changes in the future for fish populations, and then interactions between species and biodiversity in general. That will be the third aspect. And so first, to talk about the past. One particular story I want to tell you about is a lake in Japan called Lake Suwa. And this holds the longest lake ice record ever collected by man. It might actually even be the longest climate record ever collected by humans. And it's been around, this record was started in 1442. And it was started by some Japanese monks and Shinto priests. And so on this lake, there's a Shinto shrine on the lake and a monastery. And so priests for the last 15 to 17 generations have been collecting dates on when the lake freezes every year. And the reason they do that is because of cultural importance. And in particular, what they're interested in seeing is this Omiwatari. And this is this ice ridge that's formed when the lake freezes. And to the Shinto culture, this represents the time when, so there's a legend that there was a Shinto god and a goddess that lived together. And sometimes what happens when people live together too long, they got into an argument. And so the goddess moved out and she built herself a shrine on the opposite side of the lake. And so every year when the lake freezes, the god tries to make amends with the goddess, and so he crosses the lake with his dragon. And this is the dragon's tail that creates these ridges on his way to meet the goddess. And so they celebrate this with ceremonies. And it's quite an elaborate ceremony that requires purification, and it's used to project harvest as well. So will it be a good rice harvest year? And it's very important to the culture. And so all these records have been kept since 1442. So 550 years of records were kept by these priests in these journals, and we were able to get them from them. And so from there, we can look at, for example, does the lake freeze or not? And so here what we have on the x-axis is just time, so from 1443 to 2005. And on the y-axis, we have the frequency of extreme events. And that means the number of times the lake did not freeze. So that's what we're considering an extreme event. So what you see in the first 250 years of the record, the lake did not freeze 3 times in the first 250 years. In the last 50 years, the lake does not freeze 1 out of 4 years. In the last 10 years, I just got the data a few weeks ago from the Shinto priest, the lake did not freeze 5 times in the last 10 years. And so just looking at something simple as does a lake freeze or not, we can see that there's something quite different from back here to now. And so we're using this data to gather and discern other climate information. And this is just a few of the things that we're doing. And so you don't need to worry about this plot, but what I want you to look at are just these red circles outlined in black. And so what you can see in the early time period is you have a lot of these red circles in these ranges of 16, 32, 64. So these are these large-scale climate drivers that you might be familiar with, such as the solar sunspot cycle, El Nino, solar oscillation cycles, NAO, North Atlantic Oscillation, and Pacific Decadal Oscillation. Those are all represented. In the last 150 years, they're all gone. And we also have some really long ice records from Finland going back to 1693, and we see the same thing, that these large-scale climate drivers that we've been used to for thousands of years are changing. And what might be happening? So first, we're seeing a shift in the North Atlantic Oscillation. And so what it seems like is that the positive phase of the North Atlantic Oscillation is stabilized with increasing carbon dioxide, and we have a loss of these longer term cycles. Another thing that you might all be familiar with is ENSO, the El Nino Southern Oscillation Index. And back in 900 to 1300 AD, these cycles lasted 82 to 90 years. to now, they're about 2 to 8 years. So this interaction with greenhouse gases and these large-scale climate drivers are changing how what we knew, what used to be a pretty standard thing in climate, these large-scale climate drivers are also changing. So just before I leave the topic of ice, I wanted to just show you that this is not a unique feature. So this is a compilation of 150 different lakes around the Northern Hemisphere, and the number of days that the lake is melting earlier over the past 100 years. And on average, lakes are melting earlier about 1 week earlier, but range from 0 days to about 24 days. So there's variation. In the past 50 years, the blue bars here represent the rate of change. And you can see that in all these regions, Europe, Central North America, and Eastern North America, the rate of change is about 4 times faster. So something's going on in the last 50 years, and in particular the last 30 years, that really is contributing to increased rates of change in the climate. And so why might ice be melting earlier and freezing later? Well, there are 3 different things that are going on. First is climate change, and increases in air temperature and increases in carbon dioxide concentrations have been leading to earlier lake melt, and later ice formation. These large-scale climate drivers are contributing to variation in different multi-year signals, as well as local weather. So temperature, precipitation, wind events, snow cover. So all these factors put together are contributing to earlier ice melts and later ice freezes. And so what's going on with water temperature? And I'm going to talk a little bit about this collaboration that I'm a part of. It's over 80 scientists from around the world who are interested in water temperatures and have data for the past 25 years, at least the past 25 years, on measuring water temperatures in their lake. And then we've also teamed up with NASA to give us satellite records of how water temperatures have changed over the past 25 years to get a global coverage. And so these are the lakes that we've been working on. Can't really see that, but there are about 300 lakes around the world in red and yellow. And the red ones are the satellite lakes from NASA, and the yellow are the ones collected by people at the sites. And so you can see we've got a broad geographic span of lakes that we're collecting water temperatures for. And here, so the red colors represent warming water temperatures, and the blue colors represent cooling water temperatures. And what we found was that you can see a lot of red dots. And so 90% of the lakes are warming in the past 25 years. There are 10% of lakes that are actually cooling, and those happen to be in Florida, as well as the Alps. And that's because of changes to land cover. And so that's been contributing to changes. What you can see in in Ontario here, the dots are much redder than in other areas. And that's suggesting that lakes in Ontario and Canada are actually warming faster than lakes in other regions of the world. And this includes ice-covered lakes. So we're at particular risk of having these warmer lakes. And what's the consequence of warmer lakes? Well, at the base level, having increased water temperatures, lake water temperatures, changes the water quality in particular. And so you can have changes to cyanobacterial blooms and algae production, and then it goes up to fish habitat. And so the whole ecosystem can be impacted by these changing water temperatures. And so our lakes warming faster than even other regions in the world suggests that we might be at an increased risk. And around the globe, we found that there are two major drivers to these changing water temperatures. The first is climate change. So air temperatures have increased over the same time period, and that's contributing to increased water temperatures. And the second thing that we found that's probably one of the first global assessments that have documented this is something called solar brightening and dimming. And so what this means is that the northern hemisphere is becoming brighter, and we have less cloud cover than we did before. And this is in response to improved emissions and particulate emissions from industry. Whereas the southern hemisphere is becoming dimmer with more emissions and particulate matter being released into the air from increased coal production and factories in the southern hemisphere. And so what that means is that lakes in the northern hemisphere are warming even faster than what would be predicted by climate change alone. Whereas the lakes in, for example, the Tibetan Plateau and Australia are not warming as fast because of this cloud of particulate matter that seems to be influencing the atmosphere right now. So that sort of gives you an idea of what's already been happening, and hopefully I've convinced you that climate has changed by looking at lakes in terms of water temperature and lake ice, and then from there we can start developing models to project what might happen in the future to fish populations. And I'm going to tell you one story today, and the species that I chose to study for this particular study is the smallmouth bass. And if you're an angler or a fish eater, you might have heard of smallmouth bass and eaten it. It's actually a non-native warm water species to Ontario, and it was native to eastern US, but it's been expanding its range, and I'll tell you why in a few slides. And so the question that I'm interested in asking was, will smallmouth bass expand under climate change scenarios? And so why is climate change even relevant to bass? Well, it turns out that the growth rate of smallmouth bass is related to air temperatures in the summer. And so if July air temperatures are below 16 degrees Celsius, the young of the year smallmouth bass don't get to be a large enough size to successfully survive the winter. Whereas if air temperatures are above 18 degrees Celsius in July, the smallmouth bass tend to get large enough that they can survive their winter and form successful reproducing populations in following years. Well, how did bass get here in the first place? Well, many years ago, actually, Ministry of Natural Resource scientists and government officials were moving bass here. And the way they did it was through trains and planes. And so they would ride the CN rails and throw bass into the lake as they passed them. And you could fly over lakes as well and just dump bass out of the airplane as you find a lake. Anglers have been also releasing bass as they enjoy angling for it. And then bass can also move naturally through river networks. And up until 5 years ago, there was a hope that bass wouldn't cross the continental divide where all the drainage basins flow north, but that's long past now. So bass can now start traveling northward themselves. And so why are smallmouth bass even a problem? Well, when they invade a lake, many studies have shown that they're associated with reduced biodiversity. So there's been evidence of a lot fewer minnow populations when bass are in the lake because they're such voracious predators. One particular species that I was interested in is the lake trout, which is a native cold water fish, and it's a top predator and an important socioeconomically important fish. And it tends to live in the deeper portions of the lake, and it has its own fish community that it feeds on. And so typically, lake trout and bass don't share similar habitat. And so you might think, well, how can a bass impact a fish that's deep into the lake and a top predator? Well, it turns out that it happens through interactions in the food web. So in many lakes, there isn't an alternate forage fish community. And so lake trout's diet, 60% of their diet is made up of these small fishes, these small minnows, and 40% is made up of zooplankton. When bass invade a lake, they consume the majority of the minnows, and so now the lake trout's diet is shifted to 20% minnows and 80% zooplankton. And this energetically less efficient food leads to reduced growth, survival, and fecundity of lake trout populations. So these populations would be considered vulnerable. If you do have an alternate forage base available in deeper portions of the lake, in that case, the lake trout would be buffered. And so what I did, so for my master's degree, I worked on one lake, Lake Erie, and when I would be publishing my research, they would say, you need to work on more lakes. And so starting my PhD, I thought, okay, I need to work on more lakes, but I don't know how many. So I just put together a data set of 50,000 lakes and hoped that was enough, and it turned out it was. So I put together lakes with lake information, water chemistry, and fish community composition for all these lakes. And then we could get an idea of how climate change was influencing lakes across Canada. And so one of the first things I did, I'm not going to show you any of the math today, I'll just show you the maps. And first what I did was just look at where are smallmouth bass currently found. Well, in red here, this is suitable habitat. Blue is unsuitable habitat, and yellow is potential habitat. And so this map corresponds really well to where bass were actually found. And so this red region represents lakes where bass are currently found, so in southern parts of Canada. And so I used a business as usual climate change scenario and projected what might happen by 2100. And what you can see is that most of Canada could be suitable for bass by 2100 in terms of the habitat. What that also means is that cold water habitat for our important native fishes, such as lake trout, would be gone from those areas as warm water habitat seems to be in play. And so just looking at lake trout, we estimated about 10 to 20,000 lake trout populations could be threatened by the year 2100 across Canada. And actually, the smallest lakes were in biggest threat by looking at their forage fish communities. So these small lakes tended not to have complex forage fish communities and an alternate food source for lake trout to eat. They also tend to get warmest the fastest and lose oxygen levels, and so that reduces quality of habitat for these lake trout populations. I was contacted by the Ministry of Environment and Department of Fisheries and Oceans in British Columbia because they have a really important salmon fishery there. And people have been bringing smallmouth bass to their lakes. And at the time, there were 27 lakes that were invaded by smallmouth bass, and they really needed to control them. So we developed some statistical models to identify which lakes should be managed. And in particular, we were interested in lakes that had trout as well as salmon species, so that smallmouth bass did not invade those lakes. But what you can see is that 88% of the lakes that we projected would have smallmouth bass in the near future had trout populations that could be vulnerable, and 14% of salmonid populations. So it could have a huge impact on biodiversity. And so what my students have been doing over the last couple of years is looking at how climate change and invasions could influence fish community dynamics and biodiversity. So I really wanted to take some time to highlight their research since they've been working so hard on it. And so this is Miranda Chen and Thomas Van Zuyden and Samantha Stefanoff and Leanna Lopez and Checker Biswas, who've been working on developing some models. And we've updated the climate change models. Well, the IPCC has updated the climate change models in 2013. And so there are approximately, I can't see this so well, sorry. There are 20 global general circulation models, and there are different greenhouse gas emission scenarios associated with each model. And what we've developed here is looked at from blue, this is a probability of occurrence. So what is the likelihood that this fish will be here in a particular lake in 2070? So red, warm colors suggest that there's a high likelihood that the species will be there, and blue suggests that there'll be a low likelihood. And then on the left, I've had a current distribution of where the species is right now. And so this is smallmouth bass, sorry. And this is a current distribution of smallmouth bass, and it's restricted to south central Ontario. But by 2070, you can see most of this map is red, and this suggests that all the climate change scenarios, if we look at business as usual models, if we continue emitting greenhouse gases at current rates, all these lakes could potentially have smallmouth bass in them. What if we stabilize greenhouse gas emissions by 2030? Well, you see a very different scenario. Suddenly you see a lot of blue here and yellow and very little red. And so what this suggests is that if we reduce our greenhouse gas emissions, we see that smallmouth bass will not have habitat to actually persist. So, and it makes quite a big difference from going at current scenarios to stabilizing greenhouse gas emissions. I also wanted to note that between my PhD in 2007 and these models in 2013, the worst case scenario models in 2007 were just the run-of-the-mill models in 2013. So there are much worse case scenarios that they didn't even project 8 years ago. And so we wanted to look at different fishes that may change. So walleye, you may have eaten in the form, it's pickerel. Pickerel is also considered walleye, and it's an important sport fishery. And what we're projecting is a complete loss of walleye in the southern Ontario. And in the range in which it's currently highly abundant in central Ontario, they're expected to be vulnerable. And in northern Ontario, we're just projecting a range shift of walleye. And these are cool water fish species. For cold water fish species, such as Cisco, which is an important forage fish for lake trout, what you see is the complete loss of lake trout populations and Cisco populations in south central Ontario and just kind of being squeezed into northern Ontario. So I've also worked on cold water fishes at their southern end of their range in Wisconsin, and we're already seeing losses and extirpations, local extinctions of these cold water fish in their southern end of their range. So it's kind of a dire situation for these cold water species. And so if we look at, for example, smallmouth bass and walleye, so earlier I talked about smallmouth bass and lake trout, but here's smallmouth bass and walleye. What we see is that in southern Ontario, there'll be fewer walleye, and so reduced co-occurrence of walleye and bass. In central Ontario, we have predictions of increased spread of smallmouth bass, and walleye are already going to be threatened because of poor habitat. And then smallmouth bass are going to join the picture. And then in the north, there's a likelihood that there will be these novel interactions between smallmouth bass and walleye. And we modeled what the occurrence would be like. So if you look at the change in temperature for lakes in Ontario, and this is the change in co-occurrence, so this is like lakes in which walleye and bass are found together. And what you can see is after an increase of 4 degrees Celsius we have a saturation where all lakes in Ontario will have bass. And so walleye and bass may be found in similar lakes. And what we found already in Ontario in the last 10 years, this graph looks at walleye abundance. And in blue here, we have lakes in which there are no bass. And in red, we have lakes in which there are bass. And so you can see that there's 3 times less walleye in lakes where bass have already invaded. And so if this continues for lakes across Ontario, that could really change the walleye populations and their dynamics in these lakes. And so what we've been finding in our research is that smallmouth bass not only influence diversity of small fishes like minnows, but they also seem to be outcompeting native predators and iconic fishes, such as walleye and lake trout, which can have pretty big socioeconomic implications, as well as ecological implications. And what we're doing now is looking at how the community might change as a whole, like the fish community. So just in this cartoon, we can see what a lake might look like in Ontario. So we've got a number of predators, top predators, cold water predators, commercial fishes, important sport fishes, as well as a good forage fish base. And this sort of attracts tourists to come fish in this unique Canadian fishery because it's not really present in many different locations. Well, our projections under climate change scenarios suggest that what we're going to find is a lot of warm water invasive fishes, a lot of small fishes, so small forage fishes and bait fishes are projected to increase, but you see a complete loss of the cool water and the cold water predators. And we looked at the commercial fishery and the sport fishery, and we couldn't find any sign of it by 2070 under climate change scenarios. And so this iconic fishery that we have might be replaced by a fishery that you might find in Missouri or in the US, much lower latitudes than we have up here. And this could have big implications ecologically, but also economically for the fishery. And so I just want to end by talking about what we can do. So there are 2 major issues that I talked about today. The first was invasive species, and the second was greenhouse gas emissions. And the first thing we can do locally is prevent the spread of invasive species. So prevention is the best way to deal with an invader. You might have heard that the Asian carp has made its way to Canada just in the past few months. And the best way to deal with the Asian carp is to just make sure that they don't spread and don't get into any more lakes. But the same goes true for all invasive species, because once they get here, they're a lot harder to manage with their ability to move and swim and everything. The second thing we can do is mitigate greenhouse gas emissions. What our models are showing is mitigating greenhouse gas emissions can really change the type of ecosystem projections that we have. So that's things that we can all do at a local level, and then at a global level as this climate convention is starting up in Paris. And that's it, and I'll take any questions.